Hi, hello. Once again, welcoming you to the ACD narrating class for Unit 6. So, in the beginning lecture, nothing but lecture 1. Already I told you it consists of the two chapters. One is the code optimization, and the second one is the code generation. Okay, under code optimization, especially in lecture 1, we discussed the issues in the design of code optimization. Role of or position of code optimization of basic blocks. In lecture 2 we discussed about the loop optimization, people optimization and flow graphs. Okay, and this is the third lecture for the first chapter, nothing but the code optimization. So the pending topics are two. One is the principal sources of optimization, and second one is the data flow analysis of flow graphs. Okay, in this lecture we will be discussing these two topics. First one is the principal source of optimization. Okay, principal source of optimization, nothing but already we know what is the meaning of optimization. Optimization means either reducing the CPU utilization time or reducing the memory. Reducing the CPU utilization time in the sense execution is faster. Okay, we know about the optimization. And what is the meaning of principal sources of optimization in the sense? It is the one transformation technique. Transformation in the sense from one representation to another representation. Nothing but when we have the source code or intermediate code form, we are applying certain method. That method can be converting source to source or intermediate to intermediate, but with optimization way. That means either number of instructions are reduced, memory space reduced, or CPU time are reduced. So this is a meaning of principal source of optimization. I think the one transformation technique to apply the optimization. Simple word. And how we are applying that principal source of optimization. My dear, in sometimes the same concept is also called function preserving transformations. So function preserving transformation and so how we are applying this transformation technique or optimization method. So already we know about the basic block, how we are constructing the basic block based on the header choosing. How many headers we are getting, those number of basic blocks we have. Okay. When we are applying this principal source of optimization or function preserving transformation, first apply this method for the local block or local optimization. First local optimization in the sense, now observe. So it is block 1 and it may be the block 2 and there is a flow from block 1 to block 2, that is the flow graphs. Okay, so whenever you want to be apply the principle this optimization, first you must to be do the optimization for this block. When you are doing the optimization of particular this block, then only we are going to be optimized of the block 2, or then only we are going to be do the optimization of both block 1 and block 2. You got my point? And don't get the confused, nothing but when you have the two blocks, block 1 and block 2, first you must be apply the local optimization on block 1, local optimization on block 2, then only think with block 1 and block 2, or block 2 and block 1. Okay, so this is the general method we want to apply under the principal source of optimization. When you are optimizing within this block, that block in technically called local. When you are optimizing some statements, nothing but block 2 can be optimized with the help of block 1, or block 1 can be optimized with the help of block 2. Then it is called global optimization. Okay, so here in this optimization technique we are using the local as well as the global. First we are using the local, then we are using the global. Once again I am recalling what is the local optimization and what is the global optimization. Okay, now we can assuming this is our block 1 and this is our block 2, basic block 2. Now, so maybe this is our start, and block 1 to block 2, sorry, block 1 to block 2, and it may be the end. Now we can assume it in that case. When you are doing the optimization for this block only, that is the local optimization. In the same way, when you are optimizing the statements or the code or instructions under the block 2 or basic block 2 only, that is also the local optimization. And after done the local optimization for each and every basic block, when you are combined more than one basic block, that means either basic block 1 and basic block 2, in other words, when you are optimizing the instructions under block 2 by using block 1, or you are optimizing the instructions or the statements of the code under block 1 by using block 2, at that moment that optimization is technically called global. Okay, so that is the main difference between local optimization and global optimization. And in this method we have the both local and global. First we are applying the local optimization, then we are doing the global optimization. Okay, under the local optimization or function preserving transformations, we have the below functions, nothing but below optimization methods. First one, common sub-expression elimination, nothing but when you are solving your expression under the one basic block or more than one basic block, when the common sub-expression is there, so don't assign more than one temporary variable for the same sub-expression. That is the meaning of it. Okay, and copy propagation in the sense, in sometimes x is a value of 10 and anywhere y equal to x plus 20. So if these two statements under the one block, now think what is the use of assignment statement x equal to 10? Instead of using the x here in the same block, better to use 10 instead of x. Okay, so that is the meaning of copy propagation. And dead code elimination, and sometimes maybe this is your block, and you are assigning certain value for the variable. That variable may be the x and its value is the 10. Throughout your program, not in the basic block, my dear, throughout your program, you are not using this x at that moment. This x variable is technically called dead code. So when we have the dead code, you must be eliminated. If you are not eliminating the dead code, you are also allocating space for it, you are also allocating registers for it, you are also spending your CPU time for the assignment value to the variable or the register. So these are all unnecessarily waiting. Okay, that is the dead code elimination. Okay, constant folding. Constant folding is look like as a copy propagation. I think when you have the constants, like sometimes consider the one example for the constant folding. Like this is our expression, like x equal to 10 plus a into plus 20. If you are considering the actual expression is a into b plus 30. So at this moment, 10 plus 20 considered as the single constant, that is technically called constant folding. And also your copy propagation, what you have done in previous, that is also sometimes called as the constant folding. Okay, we will see these are all with one example. And be careful when you are applying these methods. Sometimes when you are doing the optimization by using common sub-expression elimination, that is also lead to once again optimizing the copy propagation. Once you done the copy propagation, maybe it is also once again cross check common sub-expression elimination. We can't predict. That means we are not optimizing only the basic block, we are optimizing global also. So that's why applying one optimization may raise opportunities for other optimizations. Okay. Don't imagine only the rises may be happen in sequence. Maybe when you are doing this one, maybe it calls the once again first one possibility. Okay, we want to be see these are all by using the one example, and most of the times asked in JNTU external examinations. And also we discussed this quick shot under unit 5 for the stack execution or runtime environment. So once again I am calling the same quick shot program, and most of the times under JNTU purpose they are asking write the 3 address code, and for this highlight or bold content and apply the constant apply the function preserving transformation techniques or peephole optimization or principal sources of optimization. My dear, in lecture 2 we discussed about the peephole optimization. If you clearly observe, peephole optimization also having the same almost also methods. Okay, so whenever you want to apply the optimization method for this one, first we must write the 3 address code for it. Okay, what is the meaning of 3 address code? What are the constraints we have? First constraint, first constraint. At most it allows 3 addresses. That is the first constraint. And second constraint, it allows only one operation on the right hand side. Be careful here. Particularly I am saying only the right hand side. Okay, so these, by using these two constraints, we are going to be write the 3 address code for this highlight plot. Okay my dear, now please be focus and concentrate. So what is our first instruction? I equal to m minus 1. Okay, when I equal to m minus 1, how many operations are there in our right side part? Only one. And one more thing is the assignment. Here some of the members are think temporary 1 equal to m minus 1, nothing but one operation on the right side, m minus 1 I am doing. Then I equal to t, nothing but it is also the constant folding, nothing but not required to define once again the constant folding or copy propagation. So that's why my advice is, when you have the only one operation on the right side, its second one is assignment, please consider as a single 3 address code instruction. You got my point? I am once again repeating. When you have the statement only one operation on the right hand side, and that right hand side value can be assigned to the left hand side variable, you must be write the single statement of its 3 address code. Okay, now observe, I equal to m minus 1. Directly I am writing my first 3 address code statement is I equal to m minus 1. And what is my second statement? J equal to n. So it is also single. So I am writing j equal to n, single statement. And now observe, third, v equal to a of n. How many operations are there in your right side part? So don't imagine only one. It has the 2 operations. One is to find the nth index. Second one is to find the corresponding element under nth rm. Then only that element is assigned to the, okay, nothing but we have the right side 2 parts. When we have the 2 partitions, it is not possible to be directly assigned for the v variable. What is the first one? N. We want to find the nth location. How we are finding the nth location? Clearly observe. This is the array, and these are the elements under this array, and our beginning address may be the 1000. When you are talking about the intermediate code form, nothing but 3 address code, we must be think about with respect of architecture. How many bytes we are allocating for this array? If it's type, I am assuming as the integer, I am assuming 64-bit architecture, and it needs the 4 bytes. So that means 1000 to 4 bytes, nothing but up to 1003 allocating the first element, 1004 onwards up to 1007 second elements, and so on for each and every 4 bytes. Okay, now I want to find the nth index. Like how I am finding this nth index? N into 4. How many elements I am requiring for this? 4, 4, 4, 4, 4. Like. Okay, so n into 4, I am getting this address. Get my point? So now our first operation is to find the nth index. So 4 into n. it is not the full operation. So that's why it is a partial result. The partial result can be assigned for the one temporary variable. This is the first temporary variable I am using in my 3 underscore. So T1 equal to 4 into n. Okay. And what is the address I have? That value of a of this address is assigned to the variable. That is my second operation. A of T1 is stored in the variable. In other words, A of T1 is assigned to the variable. Okay, we have the only one instruction v equal to A of n, but when you are writing the 3 address code, it is the two instructions. Here some of the numbers are getting set out, sir. First operation is okay, good, 4 into n. And second operation, A of n, if I am choosing one more temporary instead of v, okay, carry on at T2. Now your next operation must be the v equal to T2. Okay, the next operation is v equal to T2. That means it is also the constant folder. That's why I am simply using n into 4 is the one operation. Then E of that n into 4 temporary is assigned to the v directly like this. Okay. So up to now how many 3 address code statements I am getting? 4. Okay. Now I am going to this one. While of 1, it is the repeat until, nothing but always true. It is not possible to write the 3 address code for it. So that's why I am going for the next instruction. Do not possible. But what is the instruction here? I equal to I plus 1. So I equal to I plus 1 also directly consider as the single instruction in 3 address code, like I equal to I plus 1. And next one, clearly observe it. While A of I less than A of I less than V, it is also not the single operation. First I want to know the ith index, then A of that address is have the right to be compared with less than. Okay, if you are clearly observe here, first one find the ith index, second one find the A of I value, third one compare this A of I with, these are the 3 operations we have. Okay, so we will see how these 3 operations are writing. So A of I, nothing but first I want to find the ith index, 4 into I. Up to now I am using the only one temporary variable. Now I require the temporary 2 variable to hold the partial result, nothing but 4 into y. I am assigning for the T2. Now observe my ith index, nothing but A of T2. I am getting the one variable, one value. That value is going to be compared with B. So not possible to be directly compared with. It is the 2 operations. Find this value and compare it. So that's why I need the one more temporary variable like T3. T3 equal to of T2. Now I am getting the value of this. This value is compared with the. So if that condition may be true or false, that's why I am using the if statement conditional. So if where I am storing the A of I value, temporary variable 3, good. So T3 is less than V. Now observe. What is the meaning of this entire statement? If this condition is true, then do. Okay, condition is true, then execute the do part. That is the meaning of it. What is the beginning statement or beginning 3 address code statement for my do? Fifth one. Good. So that's why if my condition is true, T3 less than V, I must be once again repeat the do part. Do part begin with the fifth instruction. That's why go to of 5. So here once again observe, do I equal to I plus 1 while a of I less than b. That means first we will execute the equal to I plus 1, then condition checking. If condition is true, once again we are doing the I equal to I plus 1. That is the meaning or general. So that's same thing we are going to be writing our 3 address code. I equal to I plus 1, that is the instruction 5, and t2 equal to 4 into I, 6th one, t3 equal to f t2, 7th one. If t3 less than v, go to. If condition is true, I must have executed do part. From which instruction I am begin the do part, 5th one. So that's why go to 5. Good. So in the same way for the j equal to j minus 1, while I have j greater than v, so I am getting this part. Okay, now observe. Next statement is I greater than or equal to j. Break. When this statement is, this condition is true, this statement's condition is true, I must be break. Break in the sense I am not executing this part, this statement. I am breaking and I must be execute this one. I am executing this one. I am not executing this one. Okay, so now I am trying to write the code for I greater than or equal to j. Okay, these are the single values, nothing but not required to need it over temporary variables. Until now, how many temporary variables we are using? 5. Good. So directly I am writing if 13th statement, if I is greater than or equal to j, break. I don't know which 3 address code is given by x equal to a of I. So that's why I am blank target. I want to find my target. Then when I know my target, I want to rewrite its corresponding address. Next step, x equal to f. First find the ith location, then f is assigned to the x. Right. The same way here observe, f I equal to f. First know the ith index. First know the ith index, then know the jth index, then f jth index can be stored at one temporary, nothing but for knowing the ith index we require the one temporary, to know the jth index we require the one temporary, then one more temporary is required to hold the f j value. That value can be assigned to f this temporary of ith index variable. Okay, now observe how many temporary variables we are using till now? 6. So 7th one 4 into I, 8th one 4 into j, 9th one a of t8, nothing but a of this index. This index is given by t8. Okay, now a of this ith index is given by t7. A of t is followed away where I am storing this a of j value in t9. So for this value I require the 4 3 address code statements for this instruction. To now I am using the temporary variable 9. Now I am going for the a of j equal to x. A of j equal to x in the sense, once again find the jth index, then a of the value is filled with the x. It must be 3 address code informs these 2 statements. It must be. Now we are using that in temporary variable also. Until now, how many 3 address codes we are getting? 21. Now clearly observe. So this while part is over. Now we are writing the x equal to a of I. Okay. When you are writing the x equal to a of I, it is also in form of the same. First find the ith index, then x equal to a of I. Here clearly observe. why we are writing the go to of 5 here? It is a while always true, and it is the true when we are exit from the while, when we will reach this condition, when we met this condition, then only we are exit from this while. That's why the next instruction, before writing x equal to a of I, etc., the statement must be once again we enter into the while. From which address we begin our while statement? I equal to I plus 1 begin with 5. So that's why after execution of this while statement, once again we are recall the while. While is true always. While of 1 in the sense while is true always. So that's why after end of this one, for the 22, you must be right go to of this while instruction begin. While beginning 3 address code is 5. That's why we are writing go to of 5. Okay, now think about this one, x equal to a of I. This is the after while. What is our number after while loop? 23. When you are breaking or exit from your while loop, which what is your 3 address code statements number is going to be executed after 22? Nothing but 23. Okay, already for this break statement we are leaving at that moment we don't know about our target. That means what is our target now? How many 3 address code we are getting for the only while? 22. After that while we are entering into the 23. So our target must be the 23. Okay. This is also finds the ith index, and x is the I of d11, and also the same. This is required for 3 address code, and it requires the 2 address code. Nothing but that. Okay. And what about our target for this break statement? When we are getting this break statement is 13th. Here this target is replaced with the 23. Okay, so 13th way. So this is the final 3 address code we are getting. How many totally we are getting 3 address codes? 30. Okay, so these are the 33 address codes. Now when we are getting the 3 address code statements for the given source code, we want to find the leader statement or header statement. So already we know the algorithm. In that algorithm we are using the 3 rules. What is the first rule? In the given 3 address codes, the first statement itself is considered as the header statement. Nothing but by using rule 1, our first statement is leader. Now, what is our second statement? Either conditional or unconditional jump. What is our target instructions are there? Observe. How many target instructions are you getting? This is the one, 2, 3, 4, only 4. Now observe, those are all target instructions are considered as the header statements. That is given by our rule 2. Now observe rule 2. So 5, 9, 23 and 5 once again duplicate. Nothing but 5, 9, 23. 5, 9, 23. So by using rule 1, by using rule 2, 5, 9, 23. Now totally how many we are getting? 4. Now observe by using rule 3. Okay. What is our rule 3? What is the control statements we have, either conditional or unconditional in our code, after that statement is becoming as the header or a leader? Now observe. Here it is the target. What is our target? Instruction statement number 8. After that one is the 9. 9 is the leader, and here our target instruction number is the 12. After that one is the 13th. Good. Here it is the 13. After that one is the 14. Good. Nothing but our by using rule 3. In the 3 address code, what are the target instruction statements are there? After that statements becomes as the address statement. Nothing but after 8, 9 is the, and after 12, 13, and after 13, 14, and after 22, 23. Okay, 9, 13, 14 and 23 by using rule 3. 9, 13, 14 and 23. Okay, now you can write in order. If you are any duplicate, remove it. So 1, 5, 9, 13, 14, 23. So 1, 2, 3, 4, 5 and 6. Totally we have the 6. Nothing but how many header statements we are getting? 6. How many basic blocks we are getting? 6. Good. So these are the 2, 3, 4, 5 and 6. What is our first block? First block in the sense from first leader to the previous or before statement of our second leader. What is our first leader? 1. What is our second leader? 5. Before of second leader is 4. Nothing but 1 to 4. And 5 to 8. Second block. And 9 to, after 9, 13. 13 previous one is 12. Good. 9 to 12. And next one is 13. And next header is 14. 14 minus 1, 13. Nothing but 13 itself. 13 to 13. Nothing but 13 itself. Next one is 14. 14 to, next letter is the 23. 23 minus 1, 22. And the next one, 23 to last statement. There is no next letter. To last. So these are the basic blocks we are getting. 1 to 4 is the one. 5 to 8 is the second. 9 to 12 is the third one. 13 is the 14th itself. 4th itself. 14 to 22 is the 5, and 23 to last is the 6th one. So these are the basic blocks. Basic block 1, basic block 2, basic block 3, basic block 4, basic block 5, basic block 6. Now after writing the basic blocks, now try to give the flow between that basic blocks. How we are giving in the sense, observe your each and every block last statement. If its last statement is either conditional or unconditional target, go to that block. If it is not, given silence. Okay. So what is our first block last statement? V equal to f t1. It is not any target, nothing but block 1 by default gives flow to the block 2. Okay, so nothing but this one. Now observe, what about the last statement under block 2? If t3 is less than v, go to of 5. 5 is the block 2 leader, so that's why here we have the 5 actually in 3 address code. 5 in the sense block 2 leader, nothing but block 2 can be repeated itself, so that's we are representing here. Block 2 can be repeated itself. In the same way, think about the block 3. Block 3 Last statement is 12. What is the 12th statement? Go to of 9. Go to of 9 is the beginning of block 3. Once again it is a repeat itself. So block 3 can be repeated itself. Okay, block 3 can be repeated itself. Now think about the block 4. So what is the block 4 last statement? Itself. Itself it is the go to of 23. Okay, from block 4 it gives to the 23 in the sense block 6. Now observe this. Block 4 last statement is the block 6. And what about the last statement under block 5? Nothing but 22. Go to 5. Go to 5 in the sense block 2. Now observe from block 1 to block 2. Is there any flow is there? Can give it. Block 3 to block 4. Yes. Block 4 to block 5. You can give in order. So in order is compulsory, and also based on the last statement in each and every basic block you can decide its flow, which basic block it goes. Okay, observe. So block 1, block 2, block 3, block 4, block 5, and block 6. Block 1 to block 2, block 2 to block 3, block 3 to block 4, block 4 to block 5, block 5 to block 6. How we are getting? No answer. So block 1. What is the last statement? There is no any target, nothing but it follows in sequence. Okay. And what about our block 2 last statement? Go to off block 2 itself. Block 1, block 2. And after repeating the block 2 from our code, we must go to the block 3. This is our block 3. What is the last statement of block 3? Go to of 9. Nothing but that is the header statement of our block 3. Block 3 can be repeated. After repetition of this block 3, it must be goes to the block 4. Under block 4 we have the only one statement. Okay, what is the statement? If that condition is true, clearly observe, it is a condition statement. If condition is true, then go to the block 6. If condition is true, then only you are going. If condition is false, you are executing in sequence. That is our block 5. What is the last statement for block 5? Go to 5. Go to 5 in the sense basic block 2. Okay. And what is the last statement of block 6? It is not any target. So that's why it is the flow graph. It is the flow graph of our basic blocks. Nothing but finally we are getting this. Okay. Now observe. You can apply your optimization methods for individual blocks first. Block 1. Is there any common propagation is there? No. Not common sub-expression, not copy propagation, not dead code elimination, and not constant folding. The same way for the block 2 also, block 3 also, block 4 also. Now observe for the block 5. Common sub-expression. What is the common sub-expression here? 4 into y, 4 into y. How many we are assigned for the temporary? For one case we are assigned the temporary T6, and one more case we are assigned the temporary T7. Now you can remove the T7 and you can use the T6. And also in our block 5, what are the temporary variables 7? That 7 must be replaced with the T6. It must be replaced with the T6. And when you are replaced T7 with T6, this statement is duplicate and you can remove it. It is the T6. And is there any common propagation is there once again? Okay, 4 into J. Yes, this 4 into J is also the common. When it is the 4 into J is the common, what is the first temporary? T8. Here temporary is the T10. It must be removed and you must have used the T8 once again. And also all the T10s are replaced with the T8. And you must be remove this instruction. Okay. And is there any duplicate part? Is any redundancy is there? Nothing but common some expression is there? No, no, no. Okay, good. Now it is the block 5. Okay. In the same way, you can apply the block 6 also. 4 into y, you can remove it. 4 into n, you can remove it. Okay. Now, individually each and every basic block we are applying that. Now, think with respect of global. Global in the sense between basic blocks. Previously we think about the intra basic block. Now we are thinking about inter basic blocks. Now, 4 into y, yes, we have here. 4 into y, yes, we have here. 4 into y, 4 into y. Now you can observe it. Remove it. Basic block 2 to basic block 5, T2. T6 can be replaced with the T2. Okay, this is the thing we are getting. Okay. In the same way for 4 into J, you can remove it. Okay. Now observe. A of T4 is T9. Here A of T4 can be held by T5. Not required to hold once again T9. Can remove it and T9 can be replaced with the T5. Okay. And also you can apply for the same block 2 to block 6. We are getting this. So this is the common sub-expression elimination. Now we can observe. If is there any variable is assigned for anything and that variable is not used in our future, that is the dead code. That code is also, that variable is also must be eliminated. So like dead code elimination, clearly observe. X equal to T3. Nothing but if temporary 3 can be assigned to the X and X can be assigned to this, here also this. Nothing but instead of writing the X here, simply you can write the T3. Okay. And up to now we applied common sub expression elimination, dead code elimination. Nothing. Is there any possibilities there for the strength reduction? We know for the multiplication already it takes the more time than the addition. So that's why, if possible, these multiplications are replaced with addition. That is the reduction in strength. Now clearly observe these two multiplications. I am applying strength reduction. Whenever I want to apply the strength reduction, clearly observe, I must be move. It is a loop part. So actually it has the local loop. It has the local loop, and I am moving I equal to I plus 1, this multiplication outside of the loop, and this multiplication is also outside of the loop. Now it becoming as this. And here what is my I value? I equal to I plus 1. And when I am moving 4 into y, every time I am adding the only 4. So I am using temporary variable t2 equal to 4 into y and t4 equal to 4 into j. How we know this temporary variable? Okay, I am moving these two statements here, and here I equal to my this value, nothing but t2 plus 4, and here this value plus other minus 4. Okay, it is a strength reduction. If you are clearly observe, when you are applying the strength reduction, these two statements are moving outside of the loop. It is also sometimes called code motion. When you are talking about the reduction in strength, indirectly you are also talking about the code motion in this particular example. Okay, so these are the, now observe, after applying the principal sources of optimization or function preserving or people optimization, now observe how many temporary variables finally we are getting. So observe it, 1, 2, 3, 4, 5, 5, 6, only 6 temporary variables. Previously, how many temporary variables we are getting? 15 temporary variables. Now observe, lot of temporary variables we reduce. 15 to 6, nearly 60% we are reducing. Okay, nearly 60% we reduce the temporary variables. When you reduce the temporary variables space for the 60%, indirectly you are also unnecessarily, like, your CPU execution statements are also reduced. Nothing but your program execution fast. And also count how many instructions are you getting here. 6 plus 3 plus 3 plus 6, 12 plus 1, 13, 13 plus 3, 14, 14 plus 3, 17. Previously 30, nothing but here 9, temporary registers, and 13 instructions. They are not maintained. So this is the use of optimization. Unnecessary space for the 13 instructions, and unnecessary space for the 9 temporary variables, and unnecessary execution of these temporary 9 variables instructions executions So this is the code optimization. My dear, in this concept we have the so many transformation techniques are there, but well familiar one is the common sub-expression elimination. Next, think about the dead code elimination, copy propagation, constant folding. In general, if you are writing like I equal to I minus 1, if it is your source instruction, when you are writing the 3 address code, if you are using I minus 1 can be assigned with one temporary, and the temporary can be assigned with the I, then at that moment once again you must apply the copy propagation as well as the constant folding. But we are not writing in this way. That's why propagation constant folding is not effectively applied in our 3 address code. In our 3 address code, effectively applied common sub expression and dead code elimination, and also code motion. Code motion or strength reduction. Strength reduction. Strength reduction. Okay, these are the applied methods we are applying for the code optimization. So when you are applying the code optimization, especially for the basic blocks flow graph, what you are giving the connections among basic blocks, it is also called data flow analysis. Data flow analysis. Nothing but between the basic blocks, what is the data we are passing, we are also doing the optimization. Okay. So this is the syllabus of code optimization chapter regarding to our syllabus. Issues we discussed. Once again observe whether is the issues we discuss, principal sources discuss, basic blocks, okay, loop optimization, people optimization, flow graphs, data flow analysis of flow graphs. Okay, from the first chapter nothing but the code optimization. If you have any doubts, feel free to communicate with me, and also I will give you some examples of source codes. Try to write the 3 address code for those given source codes. Okay, all of you better to note one example. All of you try to write the 3 address code for dot matrix and also matrix multiplication. So it is the dot matrix and also matrix multiplication. All of you know this code and try to write your own 3 address code.